Every shift, this machine's suspension absorbs 400 tons of impact load, thousands of times, while hauling rock at 68 kilometers per hour. Fully loaded, the 797N reaches 623 metric tons, generating cyclic stresses that make fatigue, cracking its greatest structural threat. Yet it runs 20 hours a day without breaking apart. The reason isn't one system. It's how every subsystem is engineered to keep the others within their limits. Standing next to the Caterpillar 797F, ordinary vehicles vanish into insignificance. The truck's frame rises 6.5 meters above the ground, taller than a two-story house, and stretches more than 14 meters from front to back. Empty, it weighs 623 metric tons, a mass that challenges every conventional engineering rule for moving machines. But it's the tires that truly define the physical scale. Each of the six is a 5980 R63 radial, over 4 times as tall as a grown adult and weighing in at approximately 5,300 kilograms. These tires alone account for more than 30 metric tons of unsprung mass, a figure that rivals the curb weight of a city bus. Supporting such a load is only part of the equation. Each tire must carry up to 68 tons under static conditions, and far more during dynamic maneuvers, cornering, braking, or traversing uneven ground. The reinforced sidewalls and bead structure are engineered to prevent catastrophic failure when sudden impact loads spike well above design norms. Even with this robustness, tire life is finite. Under the abrasive, shifting terrain of open-pit mines, a 797F tire lasts between 6,000 and 9,000 operating hours before the risk of blowout or excessive tread wear demands replacement. The financial impact is just as imposing as the physical. A single tire costs $42,500, and replacing all 6 can approach $250,000. For mining operators, tire logistics and inventory are a constant concern. Delays in delivery or unexpected failures can sideline a truck worth over $5 million, turning each tire into both a critical engineering component and a recurring budget line. This combination of sheer mass and relentless expense sets the stage for every other system on the 797F. The drivetrain, suspension, and frame must all be designed to manage forces and costs on a scale few machines ever encounter. Maria Alvarez, lead engineer on the 797 electric drive program, stands beside the rear axle, tracing a heavy cable that runs from the engine compartment straight to the wheel hubs. At first glance, the truck's size might suggest a purely mechanical drivetrain, shafts, gears, and differentials. But the reality is a diesel-electric chain that borrows more from locomotives than from road vehicles. The core is a 4,000-horsepower CAT C17520 diesel engine, driving a 3-phase generator that produces up to 12,000 volts. This high-voltage current feeds 4 permanent magnet synchronous motors, each sealed inside a 1,200-kilogram hub assembly bolted directly to the rear wheels. Each hub motor delivers around 750 kilowatts of continuous power, roughly 1,000 horsepower per wheel, with a peak torque output of 4,500 Newton meters. The system eliminates the need for a central drive shaft and planetary gear set, reducing mechanical losses and allowing independent control of each wheel. This architecture means the 797 can apply precise torque to each rear wheel, improving traction on loose or uneven ground and enabling the truck to climb 12% grades while fully loaded. The generator's output is managed by a set of high-capacity inverters, which convert the AC supply to the exact voltage and frequency needed by each hub motor. During acceleration, the full 3,550 horsepower output is available for propulsion. On descents, those same motors instantly switch roles, acting as generators to absorb kinetic energy, a feature that will become critical when the discussion turns to braking. The entire system is monitored in real time by the truck's onboard diagnostics, which track motor temperatures, current draw, and torque output to prevent overload or thermal runaway. This electric drive is not just a technical novelty. It's a fundamental shift in how a 400-ton vehicle moves, steers, and survives in the harshest mining environments. A mining truck of this scale would be useless if its frame or axles shattered under repeated shocks. The Caterpillar 797 relies on 4 massive high-drop pneumatic suspension struts, each combining high-pressure nitrogen gas and hydraulic oil to absorb the brutal vertical impacts of hauling 400 tons across rough mine roads. Each strut is pressurized to about 250 bar, over 3,600 psi, creating a compressible gas spring that cushions the chassis from sudden jolts. When the wheels encounter a bump or a deep rut, the piston inside the strut travels up to 250 millimeters, forcing hydraulic oil through calibrated orifices. This controlled flow dissipates kinetic energy as heat, while the nitrogen compresses smoothly, preventing metal-to-metal contact and minimizing the risk of fatigue cracks in the frame. Tom Reyes, the site's safety manager, points out that the suspension must handle not just the truck's static weight but also dynamic loads that can momentarily exceed 400 metric tons per strut. During a loaded descent, the struts compress and rebound thousands of times per shift, each cycle generating heat that must be managed to avoid seal failure or oil breakdown. The struts are equipped with temperature sensors and pressure relief valves that trigger maintenance alerts if internal conditions stray outside safe limits. This level of monitoring is critical. A failed strut can transfer shock loads directly into the steel frame, accelerating the onset of fatigue cracks and threatening the truck's structural integrity. By isolating the chassis from the worst impacts, the high-drop pneumatic suspension extends the service life of both the frame and the high-cost tires. It also improves ride quality for the operator, reducing fatigue and the risk of error during long shifts. The struts are one of the few components on the 797 that are regularly rebuilt rather than replaced, with service intervals determined by cumulative load cycles and heat exposure. This approach allows the truck to maintain a predictable, controlled ride even as it absorbs millions of tons of impact over its operational life. Tom Reyes stands just behind the left rear wheel, watching as the loaded 797 begins its descent into the pit. On a 10% grade, gravity threatens to overpower friction, 400 tons of mass accelerating, with enough kinetic energy to rival a small explosion. Here, conventional brakes would overheat in minutes. Instead, each wheel hub motor instantly switches to generator mode. The retarding system absorbs up to 5,500 kilowatts of energy, converting motion into heat that is safely dissipated through resistor banks and oil-cooled exchangers. Temperatures in the retarder grid can climb past 500 degrees Celsius, but the system is engineered for continuous operation, even on the longest haul roads. The electronic controller monitors wheel speed, grade angle, and retarder oil temperature, automatically adjusting generator torque to maintain a safe descent speed. In total, the retarding force can reach 210 kilonewtons, enough to hold the truck steady on slopes where runaway is a constant threat. At the bottom, Reyes signals for a dump. 4 hydraulic cylinders, each delivering 1,500 kilonewtons of lift, raise the bed to a 55-degree angle in under 30 seconds. The entire 363-ton payload shifts and slides, but the hoist system's pressure sensors and relief valves ensure the frame absorbs only what it can safely handle. The rapid cycle time is not just about productivity. It reduces the period of maximum stress on the chassis, helping to prevent the fatigue cracks that can end a truck's working life prematurely. In these moments, the interplay of electric braking and hydraulic muscle defines the operating envelope of the 797F, setting strict limits on what the structure must endure and preparing the ground for the deeper challenge of frame fatigue. Dr. Ethan Kwan traces the seam where two steel plates meet on the 797F's main girder. The frame, built from 550 megapascals high-strength low-alloy steel, is held together by over 200 welds, each at least 10 millimeters thick. Every weld is calculated to withstand the relentless fatigue cycles of a 363-ton payload. Finite element analysis guides each joint, balancing strength against the risk of heat-affected zone softening. The weld count is not arbitrary. It's a direct response to the stresses imposed by daily operations. At full load, critical welds experience peak stresses of 250 megapascals, safely within the steel's limits, but only if the 363-ton cap is respected. Even a 10% overload can push local stresses past the steel's endurance, triggering cracks that shorten the frame's life by years. Fully loaded, the center of gravity rises 0.6 meters, amplifying bending moments and shifting stress across the spine. Caterpillar's diagnostics monitor vibration and load in real time, catching anomalies before they escalate. Dr. Kwan's team has shown that strict payload discipline dramatically reduces fatigue, crack repairs, and unscheduled downtime, making operational practice as vital as engineering. Steering a 400-ton truck through a narrow haul road demands more than brute force. Hydraulic steering delivers up to 34,000 Newton-meters of torque, enough to pivot the front wheels even when the truck is fully loaded and the tires are pressed against rough stone. The system relies on redundant hydraulic circuits and position sensors, so a loss of pressure in one line triggers an immediate transfer to a backup, keeping the truck responsive under all conditions. Every steering input is monitored by the Vehicle Health Management Suite, which also tracks oil temperature, pressure fluctuations, and actuator response times. If any reading drifts outside the safe range, the operator receives an instant warning, and the system can limit steering speed or lock out high-risk maneuvers until maintenance is performed. Tom Reyes recalls a 2019 incident at the Queensland site, when a loaded 797F began to accelerate uncontrollably down a 10% grade. The main retarder circuit had lost pressure, and for a moment the truck's mass threatened to overwhelm the brakes. But as Reyes explains, the live diagnostics flagged the drop in hydraulic pressure before the situation became critical. The park hold function activated automatically, clamping all wheels and bringing the truck to a halt just before the end of the runaway ramp. Data logs from the Vehicle Health Management System later showed that two independent pressure sensors had detected the fault within milliseconds of each other, confirming the value of sensor redundancy introduced in 2020. The incident became a case study in how layered safety nets, steering redundancy, real-time diagnostics, and automatic intervention work together to prevent disaster. In Reyes's words, "It's not just one system that saves you, it's every system talking to each other every second." As global demand for raw materials accelerates, the engineering behind these haul trucks defines the limits of modern mining. Every load, every shift, tests the balance between mass and material science. The future of extraction rests on whether these systems can keep pace or reveal new breaking points.